Okay, so this is test number 5 from series 2. This is to solidify your knowledge in waves and oscillations. The next test will be only from optics. So this test was given to solidify your knowledge on waves and oscillation as a final test on that. I have to tell you this, there are some students still who are not taking the test. If you are not going to take the test first and not going to take any action, you are never going to know the level you are in. Then you cannot improve if you don't know the level you are in. First you have to take the tests, and then you can get rid of the weaknesses that you have. First you have to know the weakness in you. That's why you need to take the test first, regardless of the amount of marks you will have. Then you can improve yourself, right? First just take the test first. Okay, moving to the first question. Sound intensity, amplitude, capital A, of R distance from a sound source are proportional in order to. Okay, first they say sound intensity. In the previous test also I explained what the sound intensity is. Intensity is power divided by area. Power divided by area. This area, if the sound source is a point sound source, this area can be considered as a area of a sphere. So the sound source is at the center. So this area is 4 pi r squared. This here A means area, right? So power divided by 4 pi r squared. So from this you can clearly see intensity is inversely proportional to r squared. So this is what they ask first. Intensity of sound is 1 over r squared. Then the amplitude. Here capital A means the amplitude. The other thing is you need to know this intensity is proportional to amplitude squared. This is not area, this is amplitude here. You have to know that intensity is proportional to amplitude squared. Okay. So if you combine these two, intensity is proportional 1 over r squared, intensity proportional amplitude squared. So these two, you can say 1 over r squared is proportional to a squared. 1 over r squared is proportional to a squared. So from this, if you take the square root, a is proportional to 1 over r. So this is the second one. So intensity is 1 over r squared, amplitude is 1 over r. So the answer for that should be the second one for the first question. The second question. Two progressive waves move into opposite directions, each with frequency 100 Hz, superpose to make a standing wave. Distance between consecutive antinode and a node is 8 cm. Speed of the progressive wave is. So these are like we know that when making standing waves, it's a result of superposition of two progressive waves. So the frequency of the standing wave also will be the frequency of the progressive waves. Okay, now we know the frequency of the standing wave, that is 100 Hz. Let's say those two created a standing wave like this. Let's say this could have many loops more than this. This is just for example. Then they have given a distance between consecutive antinode and a node. So this is a antinode, this is a node. they have given this distance as 8 centimeters. So we know that this amount of distance is 1/4 of a wavelength. I mean, this from here to here, it is a lambda over 2. Half of it is lambda over 4. So we know that lambda over 4 is equal to 8 centimeters. So lambda is equal to 32 centimeters. In meters, this is 0.32 meters. You have to divide by 100. 0.32 meters. Then we know the frequency, then simply apply V equals F lambda. So this V equals F lambda is like F equals ma. In mechanics, we always have to apply this equation in waves and oscillations. So what they ask is speed of the wave. We know the F, that is 100, lambda is 0.32. So 32 meters per second. This is the speed of the wave. So the answer for the second question should be fifth one. Third question. Phase difference of 2 points close to the node on either side of it in a standing wave is. So I'll just draw a standing wave with like 3 loops for an example. So what they ask is, so this is a node, either side of the node close to, let's say this point and this point. So what they ask is phase difference between 2 points. So like many students don't understand the difference between those phases in a standing wave and in a progressive wave. If I take a progressive wave like this, so this is just a progressive wave. How do we know the phase of that? Let's say this point is at phase 0. Then this point will be at 90 degrees of phase, 5/2. Then this is 5. And this will be 3/5/2. So this is 270 degrees. This is 180. Here it will be 360 or 25. So you can see each point of a progressive wave, phase increases. For each point, phase increases. You can draw a circle and figure it out like this. Let's say you drew the circle like this. So if you think about a phase of this point has phase this much. It's kind of like 30 degrees, let's say. So this point is at a phase 30 degrees. And if you think about this point, it has a phase 90 degrees. Then this point 180. Then this point 270. 390s, so it is 270. Then again, if you go for this point, it completes a one cycle. It goes to 360 degrees. So by drawing a circle, you can understand, you can determine the phase of that particular point. Phase of that point. That related angle is the phase of that point. But if you think about a standing wave, so you know that the circle, radius of the circle should be amplitude. So here this point has amplitude, these have smaller amplitudes. These have a small amplitude. If you drew a circle, that circle would be a smaller circle. So the phase of this point at the peak is 90 degrees. this point also has a 90 degrees. So you have to draw a bigger circle for that. This point, you need to draw another circle for that, because it has a different amplitude. Each point has different amplitudes. Amplitude keep increasing. At the antinode, it has the highest maximum amplitude. It has a maximum amplitude. As you can see, all these points are at like 90 degree phase of all the points in a one loop, 90 degrees. And here all the points should be at 180 degrees. No, sorry, 270 degrees. All the points, you can draw different circles for each points, and you can see that it completes a 270 degrees. That's the key difference between standing waves and progressive waves. So for standing waves, you have to draw circles, like bunch of circles related to their amplitude. So what's the difference? 270 minus 90. So the difference should be 180. Just remember, all the points of a one loop is at the same phase in a standing wave. Then the other loop, close to that loop, another loop, it is at the opposite phase always. So the phase difference between these 2 points of the each loop is 180 degrees. It is always like difference is 180 degrees. So always other loop, all the points of the other loop is at a phase difference of 180. They are the opposite phase always. Okay, so that is the consecutive loop. So the phase difference is 180 always. Okay, the answer should be the fifth one for the third question. Fourth question. 24 musical forks are arranged to ascending order of their frequency. When any two consecutive musical forks are vibrated, 4 Hz of beat frequency can be heard. If the frequency of last musical fork is twice the frequency of first musical fork, the frequency of the last musical fork is. So this is looks complicated, but easy question if you clearly understand that. Before drawing like 20 musical forks, I'll just draw 3 musical forks. Let's say these are the 3 musical forks. So if there are 3 musical forks, the number of gaps is 2. If there are 4 musical forks, the number of gaps should be 3. So if there are 24 musical forks, the number of gaps should be 23. The gaps is what creates the gaps, or the differences of frequencies is what creates the beats. So there are 23 gaps if there are 24 musical forks. So let's say the first musical fork has frequency simple F. Then the last one should have what? Simple F plus. Number of gaps is 23. So the frequency difference should be 23 times 4. One gap is 4. 4 times 23. So the frequency of the last musical fork should be this much. And in the question further they say frequency of the last musical fork is twice the frequency of the first musical fork. So we have written the frequency of last fork in two different ways according to the question. Then these two must be same. So we can write simply 2f equals f plus 23 times 4. So just simplify the equation, minus f 23 times 4, 12, 9. So it is 92 hertz. Simple f is 92 hertz. So this is not the answer, right? Simple f is the frequency of the first musical fork, but what they ask is frequency of last musical fork. So the that is f plus this 23 times 4. F is we found to be 92 plus this also is 92. So the answer should be 180. 184 hertz should be the frequency of the last musical fork. So the answer is fourth one for the fourth question. Fifth question. In a medium, wavelength of a wave with speed 3 times 10 to the power 8 is 450 nanometers. When it enters a medium with refractive index 1.5, its speed and wavelength in order are. So this could be air or a vacuum. Then the wave enters a medium with refractive index 1.5. So I'll explain this further in optics. For now, you know this equation, n equals c divided by v. C is the speed of light in a vacuum, or approximately air. Then v is velocity in the medium. Then for c we can apply c is equal to f lambda. I'm just basically applying this equation. So instead of c I can say frequency of light, then lambda is, I'll put lambda naught for the wavelength of the wave in vacuum. So this v is speed of light in the medium. So in the medium, when the wave enters another medium, the frequency does not change. Frequency is only dependent on the source. So if you need to change the frequency, you need to change the source. But here the source is not changing. Only the medium changes. So the frequency is still simple f. But the wavelength change. Let's say the wavelength in that medium is lambda 1. So here lambda naught, here lambda 1. So you can just use these two equations to figure out the speed and all those things. So here n is 1.5, c is 3 times 10 to the power 8, v cross multiply 1.5. So this is 1.53 means 2 1.5s. 2 times 10 to the power 8 meters per second. So this is the speed of the wave in the medium. Then we need wavelength. This simple f cancels off because same frequency. Then I'll use this equation, lambda naught divided by lambda 1. 1.5 lambda naught is wavelength here in the vacuum is given as 450 nanometers. Lambda 1. Keep it like nanometers. You will get the answer in nanometers as well. So lambda 1 is equal to 45 divided by 1.5. So this should be 330, like 45 has 31.5s, then there's the 0, then it becomes 300 nanometers. This is the wavelength in the medium. Not in the medium, I mean wavelength of the wave in the medium. So velocity is decreased to this much, 2 times 10 to the power 8, and wavelength also has decreased to 300 nanometers in the medium. So the answer for that should be the third one for the 5th question. Right, 6th question. When two musical forks A and B are vibrated simultaneously, beat frequency heard is 7 Hz. When fork A is applied wax and the forks are played, beat frequency heard is 5 Hz. If frequency of fork B is 300 Hz, frequency of A after wax applied is. Okay, so we have two musical forks. When you get a question like this, you have to follow these steps, so you'll always get the correct answer. Okay, so we have two musical forks. They are A and B. So I'm going to put frequency levels here. So the frequency of B is given as 300 Hz. It is given. You cannot change that. Frequency of B is given as 300 Hz. Right. Then if frequency of B is definitely 300 Hz, then they say without applying wax, before applying wax, there are two possible values for frequency of A in order to make beats of 7. So this A could have this frequency 307, or this could have 293 Hz. So there are two possible values for A. The goal here is to find which one is the correct frequency. So to figure it out, we need another detail. Then the next part, they say when A is applied wax, beat frequency decreased to 5 Hz. So when wax is applied, always the frequency drops. Let's say A is applied wax, so frequency dropped here. If this is the situation, if A is applied wax, frequency dropped to this level, and they have given the beat frequency now. Now the beat frequency is 5 Hz. So this could be 5 Hz. Can this be 5 Hz? Now if this is the correct case, the beat frequency now should be more than 7 Hz. It should be more than 7 Hz. So we can conclude the only matching case is this case. So this is the only matching case. With the details, this is the only scenario that matches. Right. So what they ask is, this is the frequency of A, frequency level of A after wax is applied. Now this frequency is 300. Now the beat frequency is 5 Hz. So after wax is applied, frequency of A should be 305 Hz. 305 Hz. So this is before applying the wax. Frequency of A is 307. We chose that to be the correct one. This is not possible. This is the possible case. Then after wax is applied, the frequency of A dropped to 305 Hz. So this is the pattern. You have to practice these kinds of questions. Once you have the practice, these are not that hard, right? So the answer should be second one for the sixth question. Right, seventh question. Two sound waves in air with wavelengths 68,176 meters, 68,174 meters produce a beat frequency of 5 Hz with another sound separately. Sound speed in air is, right. So with another sound, let's say this is the another sound. We don't know the frequency of that sound, another sound, right? So let's say the frequency is F. So we know this one as well. Frequency is inversely proportional to the length. We know that as well. So one wave creates a beat frequency 5 Hz. So it has the higher frequency. So the frequency of this should be F plus 5. According to this higher frequency should have the lower length. Higher the frequency, less the length. So the less length is 68 divided by 176 meters. If the denominator is large, the value is smaller. Then for the another wave, its frequency should be 5 Hz less. So here the frequency should be F minus 5. If the frequency is less, length should be higher. So the higher length should be the another one, 68 divided by 174. If this is less, value is higher. So now we have this. If you can think about this case, F plus 5 is proportional to 1 over this length. We are using this one. So that is 68 divided by 176. If you like flip that, this becomes 176 divided by 68. We'll just keep that. Then I'm choosing this case, that is F minus 5 proportional to 1 over 68 over 174. Then you can flip that. 174 divided by 68. Now we have two cases. I'm going to divide those 1 by 2. So this is F plus 5 divided by F minus 5 equal to 176 divided by 68 divided by 174 divided by 68. So you can get rid of 68 if you multiply both denominator and numerator by 68. So this is 176, 174. F plus 5 divided by F minus 5. I'll further simplify this by dividing by 2. So this is 8, 8, 8, 7. So 88 divided by 87. F plus 5, F minus 5. Then cross multiply. 87 F plus 87 5 equals 88 F minus 88 5. So this is you can subtract this if you bring it to here. So this becomes F. Then you can take this to the other side. 87 times 5 plus 88 times 5. Take 5 out. This becomes 87 plus 88. The frequency is 87, that is 15. 1 is remaining, 70 times 5. So the frequency if you simplify that, frequency should be 5 times 5, 25, 2 is remaining, 5 times 7, 35, 37, 3 is remaining, 85. So this is the simple f. Now we found the simple f. The calculation is kind of like bit complicated. So the frequency of the other sound source is 875. So what they ask here is what do they ask? What they ask is not the frequency. What they ask is the speed of the sound. We know the value of simple f. We know the value of simple f. That is 875. Then I'm going to apply. So this is, we found that 875 hertz frequency of this. Then the frequency of this should be 875 plus 5. So it should be 880. Frequency of this should be 880. Now we know the frequency of this and the wavelength of this. This is the wavelength. So if we know the frequency and the wavelength, just apply V equals F lambda to this case. Okay, here just so we found this frequency. Then just apply V equals F lambda to this case. So the frequency of this case is 880. Wavelength is 68 divided by 176. So this is 34, 8, 8. 8 means you can just cancel this off. 10 times 34, that is 340 meters per second exactly. So this is the velocity of the sound. So the answer should be the third one for 7th question. 8th question. An observer moves twice the speed of sound towards a sound source emitting sound at frequency 1 kilohertz. Apparent frequency is, right? So let's say we have this source and we have the observer. So the observer moves at twice the speed of sound towards the sound source. So if the velocity of sound is v, velocity of the observer is 2v. Velocity of the observer is 2v, twice the speed. This has a frequency, let's say that is f naught, 1 kilohertz, so 1000 hertz. That's the frequency of the source, right? So from source the sound waves are coming towards the observer at the speed v, and the observer is moving towards the sound source at 2v. So this is the scenario, right? There's this easy equation to find the apparent frequency. I have done this earlier. VSO divided by VSS times F naught. VSO means sound speed relative to observer. This is sound speed relative to source. This S is source, right? This S is sound. This is observer, this is source. So sound speed relative to observer. So sound is moving to this side, observer is moving to this side. So the relative velocity should be the addition of these two, v plus 2v. Then this is sound speed relative to source. Source is at rest, So the relative velocity of sound is just v times actual frequency, real frequency, that is f naught. It is given as 1000 hertz. So this is 3v divided by v times 1000, 3 times 1000, 3000 hertz or 3 kilohertz. So the apparent frequency heard by the observer or the experienced by the observer is 3 kilohertz. So the answer should be the fourth one for the 8th question. Okay, ninth question. Ratio between apparent frequencies as a sound wave moving at n times the sound velocity towards and sound frequency from a fixed and then passing from a fixed observer is. Okay, here the sound source is moving, so this is the observer. Here it is the observer. First sound source is moving towards the observer, and then sound source is moving away from the observer. Observer is at rest. Velocity of the source is nv. This also is nv, and they say n is less than 1, and the velocity of sound is v. Here the velocity sound wave is towards the observer. Here also sound wave is towards the observer. Here the source is moving towards the observer. Here the source is moving away from the observer. When the source is moving towards the observer, let's say the apparent frequency heard is f-1. If source is moving away from the observer, let's say apparent frequency heard is f2 dash. So what they ask is a ratio between these two, ratio between those two. For that, you first have to find each of these apparent frequencies, right? So we'll find this one first. So what's the equation? VSO VSS, velocity of sound relative to observer, velocity of sound relative to source. Okay, first this case means moving towards the observer. Velocity of sound relative to observer. Observer is at rest, so the velocity of sound is just velocity of sound, that is v. Then velocity of sound relative to source. Source is moving and the sound also is moving to the same side, so the relative velocity should be difference between these two, so that should be v minus nv times f naught. F naught is the actual frequency of the source. I just took it like f naught. Here v divided by, I can take v from this one out, and f naught, then cancel v, then this becomes f naught divided by 1 minus n. So this is f1 dash, apparent frequency as the source towards the observer. Then let's do the same thing when it is moving away from the observer, that is f2 dash, right? So VSO VSS f naught, sound velocity relative to observer. Observer is at rest, so his sound velocity is just v. Sound velocity relative to source. source is moving away, sound is moving to this side, so these two are opposite directions. So the relative velocity should be the sum of these two. So it is v plus nv times f naught. Then you can say, if you get rid of v, this becomes this much. So this is f naught divided by n plus 1 or 1 plus n. So we have first one and second one. What they ask is ratio between these two. So just 1 divided by 2. f1 dash divided by f2 dash equals f naught 1 minus n divided by f naught 1 plus n. F naught cancels off. So this just flips. This is the main division. This just flips. So this goes to the numerator, this comes to the denominator. So this is the ratio between these apparent frequencies, 1 plus n divided by 1 minus n. So the answer should be the fourth one for 9th question. 10th question. An ambulance moves at 2 meters per second, emitting sound from its siren at 700 Hz towards the wall. Given that the sound velocity is 350 meters per second, beat frequency heard by the driver of ambulance is. So we have this ambulance. This is actually the sound source, and it has a velocity 2 meters per second moving towards the wall. So let's say this is the wall. Real frequency emitted by the ambulance is 700 Hz. Is the actual frequency, and the sound velocity is given as 350 meters per second. Beat frequency heard by the driver of ambulance is. So you have to think, how can the driver hears a beat frequency? In order to hear a beat frequency, you need to have two different sound sources, and there should be a slight difference between the frequency of those sound sources. That difference should be less than 10, otherwise you wouldn't hear the beats. So the driver is here. So what is the other sound source? So 700 Hz, that is a one sound source heard by the driver in the ambulance. Then the another sound source should be, once it hits the wall, once the sound waves hits this wall, and it reflects off the wall and comes back with a slightly different frequency. Then that frequency and this frequency is going to create beats. Let's see how that happens. Right. So this sound wave is moving towards the wall. Here you can say wall acts as observer. Wall acts as observer. This is the source, this is the observer for the first case, because the wall is receiving the sound waves. So this is going to be the observer temporarily. Right. So the wall is not going to receive the apparent frequency, real frequency 700. Since the source is moving, it is going to hear an apparent frequency, let's say f dash. Right. First I'll calculate f dash. So this is the source, this is the observer. VSO, VSS, F naught. Okay. sound velocity relative to observer. Observer, that is wall, it is at rest, so the sound velocity is just going to be 350. Sound velocity relative to source. Source and the sound is moving to the same direction, so relative velocity should be the difference. So it's going to be 350 minus 2 times f naught, frequency of the actual frequency of the sound wave. So I'll put it as like 700. Okay, so this is f dash. Okay, that is done. Then what happens? This sound wave reflects off this wall. You know, when reflection happens, frequency does not change. So this is the incident frequency. Reflected frequency also is going to be f dash. Then it is moving to this side. But since this is moving, that frequency again is going to change. Let's say that's going to f double dash. That changed to f double dash. The next thing is, now wall is releasing sound, so it is like the source now. Ambulance is like the observer. Since he is receiving the sound waves, in this case ambulance is going to be the observer, wall is going to be the source. Right, source, observer, don't mix it up. Source, observer, wall is now the source. Previous case, wall was the receiving end, was at the receiving end, so it became the observer. Now wall is emitting, it is like emitting sound, so this becomes the source, this becomes the observer. Right, again use the same equation, f double dash VSO VSS. Now the frequency of the sound wave is f dash, not f naught. Source is emitting sound with frequency f dash, not f naught, so this is f dash. Right, VSO, sound velocity relative to observer. Observer is at rest, now the sound is moving to this direction at 350, so it's just going to be 350 since the source is at rest. Relative to the observer, right? Sound velocity relative to the observer. Observer is moving to this side, so it's going to be 2 meters per second. Then the sound is coming to this side, opposite directions. 350 plus 2 divided by VSS. Sound velocity relative to source. Source is at rest. Sound velocity is just going to be 350 times f dash. So we got an expression for f dash. I'll just substitute it here. So I'll put it like 352, 350. F dash is this much. 350 divided by, if you subtract this, 348 times 700, right? 700. Then I'll just cancel these two. So this becomes 352 times 700 divided by 348. If you want, you can further simplify this. Okay, now we have an expression for f double dash, this much. So what's going to be the beat frequency heard by the driver? Driver hears this frequency. It is the frequency of the siren of the ambulance, and the reflected one is f double dash. So the beat frequency is going to be f double dash minus actual frequency, f naught. So f double dash, this is the value, 352 700 divided by 348 minus f naught is 700. I'll take 700 out. 352 348 minus 1 1 7 6 1 7 4, again divided by 2, 8 8 8 7. So 788 divided by 87 minus 1, 88, get the common denominator, 87 divided by 87. So 700 times 1 divided by 87. So the beat frequency should be 700 divided by 87. 700 divided by 87. So it is 8.04. If this is too hard, you can use logarithms. So it is going to be 8.04 hertz. So the approximately the beat frequency should be 8 hertz. So that's the answer for the 10th question. Right, 11th question. A man P is at a distance 600 meters from a train station S. This is the man, 600 meters. A train moving at 72 kilometers per hour. So there's, you have the train, is at a distance 800 meters. 72 kilometers per hour, just convert it to meters per second. 5 divided by 18. How many? 4. So this is 20 meters per second. That's the velocity of the train. So 20 meters per second, this is the velocity of the train. Train is moving to the station, right? Not towards the man, towards the station. The man is here. So here the difference, only difference compared to the previous questions is source. This is the source actually. Source is moving to this side, but the sound waves are moving to the direction of the man. Sound waves are moving to the all the directions, but relevant sound wave, because the sound wave is heard by the man, right? So the sound wave is moving towards the man because he is hearing the sound. We only need this wave. So that sound wave is velocity, it has 340 meters per second. This is the velocity of sound towards the man. And the actual frequency, real frequency, is given as 800 hertz, that is f naught. So what they ask is apparent frequency heard by the man is. So here, whenever you have a case like this, case means direction of the source is to one side, but the direction of the sound is to another side. What you have to do is, here we have the observer. This is the source actually. This is the source. This is the observer. Just draw this line between observer and source. Then let's say this angle is theta. Project all the components onto this line. Onto this line. Right. So velocity is towards the station of the source, but what is relevant is the component towards this line. along this line. So it's going to be 20 cos theta. That's all you have to do. Now you can think the train is moving to this direction at 20 cos theta, or the train or the source is moving towards the man at 20 cos theta speed or velocity. It's actually moving to this direction, but what is relevant to the apparent frequency is the component towards this line. Everything happens along this line for apparent frequency. When you are finding apparent frequency, what matters is the line between observer and the source, and whatever the direction they move, right? So everything should be along this line. Then there's no difference to the other questions. F dash is VSO divided by VSS times F naught. Sound velocity relative to the observer. Observer is at rest, so the relativity of observer sound velocity is going to be just 340. Sound velocity relative to source. Source is moving to this direction, and the sound velocity also is moving to the same direction. So the relative velocity should be difference between these two, this one and this one, not 20. It is 20 cos theta. So this is 340 minus 20 cos theta times actual frequency that they have given as 800 hertz. So this is 340 divided by 340 minus 20. Other thing is we need to find a value for cos theta. So to find that, I'm going to use this triangle. If I separate draw that, if this is 800 and this is 600, this should be 1000. Just forget about these zeros. 36 squared, sorry, 6 squared 36, 8 squared 64. So it's going to be 100. 100 root of this should be the length of the hypotenuse. So it's just going to be 1000, right? So this is theta, but what we need is cos theta. Cos theta is adjacent divided by hypotenuse, so it is 800 divided by 1000. 2, 2, 4, 5. So cos theta is 4 over 5. Just substitute it here. So 5 means 1, 4, 16 times 800. So just have to simplify this. 340 minus 16, 36, 326, 800. Okay, just divide this 16 by 2, 163, 400. If it is complicated, you can use logarithms. So the answer for that should be 839.5 hertz. That is the exact answer. So the answer for that should be 11th. For the 11th question should be the second one, 839.5. Right. 12th question. A star moving at 100 kilometers per second away from Earth emits light with with wavelength 570 nanometers. Change of wavelength due to motion of star is, right? So this is, let's say this is the Earth. Earth is receiving light from the star, and star is moving away at 100 kilometers per second. It means kilo means 10 to the power 3 times 10 to the power 2, that should be 10 to the power 5 meters per second. Let's say that velocity is like simple v, so it is moving away from the earth, and the wavelength, this is the actual wavelength of light, emitted by the star, is 570 nanometers. Let's say that is lambda naught. Then light speed, I'll take it as simple c, speed of light. They have given a value for that, 3 times 10 to the power 8 meters per second. 3 times 10 to the power 8 meters per second. Okay, so those are the data, right? So what they ask is, as this light reaches earth, change of frequency. So since due to the motion of the star, the earth cannot receive the light with the actual frequency, actual wavelength. So it receives an apparent wavelength. So let's say that is lambda dash. So we have to find lambda dash. So in this case, this is the source, star is the source, this is the observer, earth is the observer. So there are like two things. If you think about velocity and wavelength, if velocity to be changed to a different value when it goes to the apparent velocity, it is dependent on the observer. Wavelength is dependent on the source only. Just remember that these are the basics. Velocity is dependent on the observer, apparent velocity. Apparent wavelength is dependent on the source only. So we can neglect, since we are finding apparent wavelength, we can neglect the speed of the earth. Then we can find lambda dash. So lambda dash is equal to, light is moving to this direction and the star is moving to this direction. So per second it is 10 to the power 5, here 3 times 10 to the power 8. Then that amount is divided into actual number of, that distance is divided into actual number of frequency. Let's say the actual frequency is f0. So this is what you have to do. C plus, C means to this side per second, to this side V. So C plus V divided by actual frequency, that is f0. So if you apply this equation, V equals f lambda, here the V is C, actual frequency f0, lambda is actual lambda, true lambda. Then for f0 you can say C divided by lambda naught. So C plus V divided by f0 is C divided by lambda naught. C plus V divided by C, lambda naught goes here, lambda dash. So here I'm going to first derive an expression, right? Derive an equation, then do the substitution to get the answer here. So here I'll just divide this by C, 1 plus V divided by C, lambda naught. This is lambda dash. So lambda dash equals lambda naught plus lambda naught V divided by C. Then take it to other side, lambda dash minus lambda naught equals lambda naught V divided by C. So this is the change of wavelength. So we have this expression for the change of wavelength, that is lambda naught V divided by C, right? So once we get this expression, we can find the change of wavelength. So that is lambda naught is given as 570 nanometers. V is 10 to the power 5. C is 3 times 10 to the power 8. 193 10 to the power minus 3, 0.190 nanometers. This is the change of wavelength. So the actual wavelength is 570 nanometers. Due to motion of the star, the wavelength got deviated from this amount, 0.190 nanometers. So this is how they find those velocity of the stars, and whether the star is moving away or moving towards the earth. Normally we call that that is why those spectrum coming from stars gets red shifted sometimes and blue shifted sometimes. This is the reason. So this is how you find the shifted amount of wavelength. So you have practice doing this, right? So the answer for that should be the second one to the 12th question. Right. 13th question. When the sound speed is V, two pipes with length L are vibrated with their fundamental frequencies. Then length of one pipe is reduced by Y. Y is like very small to capital L. Now the beat frequency is, right. So we have two pipes. Length of one pipe is capital L. Length of another pipe is L minus Y, since its length is reduced by Y amount. Also they say that Y amount is like very small. Then they are vibrated at their fundamental frequencies. So the fundamental for these are open pipes. Actually they should mention whether this is open or not. Let's take this to be open. So the fundamental should be like this. Fundamental wave patterns. So one of these is lambda over 4. Lambda over 4. So we have 2 lambda over 4s. 2 means lambda over 2. So length of this also is lambda over 2. So lambda over 2 is equal capital L here. So lambda for this case is equal to 2L. This also is lambda over 2. Let's say lambda dash. This length lambda dash over 2 equals, now the length is L minus Y. So lambda dash is 2L minus Y. So now we found the wavelengths. Then let's find frequency. Frequency, I'm just applying V equals F lambda. So frequency is V divided by lambda. Here V divided by lambda is equal to 2L. Let's say this is frequency is F1. Here F2, sound velocity does not change, so it is still V. Lambda, here it is lambda dash, it is 2L minus Y. So these are the two frequencies created by each. Right. So the beat frequency should be F2 minus F1. So F2 is this value, V divided by 2L minus Y, minus F1 is this, V divided by 2L. I'll take V divided by 2 out from each. What is remaining is 1 divided by L minus Y minus 1 divided by capital L. V over 2 L minus Y times L. Get the common denominator L minus Y. V over 2 L minus L cancels off, minus minus plus Y divided by L minus Y. So that is what you get for FB. You can further simplify this using this approximation. So here FB is V over 2 Y divided by L minus Y. Since they say Y is very small compared to L, meaning if you like reduce amount of Y, L wouldn't be effective. It still will be capital L. It is like if you reduce 1 meter, let's say that L is 1 meter, and if you reduce like 1 millimeter from a 1 meter, it doesn't affect that much. So we can consider this to be 1 millimeter still. Similarly, so L minus Y is approximately we can consider to be capital L. So instead of this one, I can put capital L. So FB is V over 2 Y divided by L. This also is capital L. Vy divided by 2L squared. This is the beat frequency. Vy divided by 2L squared. So 13 for the 13th question, it's going to be third one. So you have to practice doing these approximations. In A levels as well, they have given such approximations like frequently. So you have to practice for these approximations, right? You can check the papers. There are many cases that these you will have to use these approximations. So you have to pay attention to these as well, right? If you need to score full marks. Okay, the answer is third one for the 13th question. Right, 14th question. If intensity of a sound is doubled, increase of its intensity level is, right? So for the intensity level, this is the equation. This I naught here is threshold intensity, 10 to the power minus 12 for human ear, 10 to the power minus. So we can solve the question using this as well. But here they say like you have to compare intensity of two instances, like one intensity is I, other intensity is 2I. Intensity is doubled. So in such cases you have to remember this equation, delta B, not B, change of intensity level. So increase or decrease, that is a change. So this equation is similar to this one. There's a slight difference, but I1 divided by I2. I1 and I2 are the intensities at two different cases. We can like prove this one, right? Write the same thing twice and take you just have to do a simple calculation to get the change. Here the intensities here is not the threshold intensity. Threshold intensity cancels off. These are the intensity at two cases. Like in many MCQs, you will have to use this equation, not this equation, right? Right. So delta B, they are asking for the increase 10 log 10. So at the second case, intensity is doubled, so this should be 2i. The previous case should be I. So I cancels off, then what happens? 10 log 10, 2. For this one, a value is given as 0.3. 10 times 0.3. So this is going to be 3 decibels. So this is delta beta. Delta beta, this is the increase of intensity level if the sound intensity doubles. When sound intensity doubles, intensity level also does not double, right? It is just increased by 3 times because this is a log scale, right? So the answer for the 14th one should be the third one. Okay, 15th question. A violin causes a sound intensity level of 60 decibel at a place. If 16 such identical violins are played, sound intensity level caused at the place is, right? For this one as well, you have to compare two cases, one violin and 16 violins. So if one violin creates intensity of I, 16 violin creates intensity of 16I. I and 16I. So these are the two things you have to compare. So whenever you have to compare, it is easy to use this equation. Delta beta 10 log I2 divided by I1. I2 divided by I1. These are the intensities of two cases. So first find the change of intensity level. This is the change of intensity. I is increased to 16 times I. But what they ask is about something like intensity level, right? So 10 log 10. I2 is 16I. Initially, I is just I. So first, let's find a increase of intensity level. If you cancel these two, this becomes 16. 10 log 10. Log 16 is not given. So what can we do? Only log 2 is given. I can write this 16 as like this, 2 to the power 4. Then you can take this 4 in front of log. These were in O levels, right? 4 times log 10, 2. So this is 10 to the power 4, that is, sorry, 10 times 4, that is 40, times log 10, 2 means 0.3, it is given. So 3 times 4, that is 12 decibels. Okay, so increase of this intensity level is 12 decibels. Increase of 12 decibel. One violin causes a 60 decibel intensity level, 60 decibel, but that should be increased by 12 decibel if you have 16 violins. So it says 16 violins, sorry, increased by 12 decibels if you have. So initial intensity level is 60 decibels. For 16 violins, increase, this is delta beta, this is beta. So you have to add these two to get the new intensity level. So it should be 72 decibels. So the answer for the 15th question should be the